Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will discuss about some tutorial questions in the Module 3, which is on the basic finite difference method. So in the previous sessions, we have seen basically what is forward, backward, and central difference using the Taylor series of expansion. So in today's session, we will see basically how do we get the second order derivatives. So what what are the steps to be seen to get the second order derivative? So this is one part of the tutorial question. So that is derive the finite difference method for the second order derivative term. So to express in terms of index notation. So this is the part of the question, so which we will discuss in today's session. Okay, so before that, just recap about the Taylor series of expansion and why, because those basic steps, the forward and backward difference, are those important formulas which are required to develop the formulation for the higher order derivatives. Okay, so therefore let's see. So basically, what is forward difference? What is backward difference? Once again, using Taylor series of expansion. So basically, forward difference. So let's say, so we will see f of x plus delta x. So using Taylor series of expansion, we will do so f of x plus dou f by dou x into f of x delta x divided by 1 factorial plus dou square f by dou x square. Okay. So delta x square by 2 factorial plus dou cube of f of x divided by dou x cube into delta x cube divided by 3 factorial plus so on. Okay. So this is what we have for the forward difference. Similarly, we need to see for the backward difference actually. Okay. So f of x minus delta x. So here you can see the formulation. So f of x, next the odd derivative terms will have the negative symbol, and the even derivative terms, they will have a positive symbol, minus dou f of x by dou x into delta x divided by 1 factorial plus dou square f of x divided by dou x square into delta x square divided by 2 factorial minus dou cube f of x divided by dou x cube to delta x cube divided by 3 factorial plus so on. Okay, so here you can see the negative terms in the order term, and for the first equation, so let us take this as equation 1 and equation 2. So in these two equations, the difference is for the odd derivative term in the second equation has the negative symbol, and even derivative term, they have the positive symbol as we have. So now if we actually take equation 1, so how do we write forward difference? So basically, if you take equation 1, from equation 1, so if we rearrange, so f of x plus delta x minus f of x, okay, so divided by delta x, okay, next minus, so what are the terms which we take it here? So dou square f of x divided by dou x square into delta x divided by 2 factorial plus so on is equal to dou f by dou x. So here you can see, so this higher order terms, basically whatever we have written, so this is called TE terms, which is truncation error terms. So these are called TE terms, which is truncation error terms. So we will neglect these terms and we will place it as higher order terms. So now if we want to define, so what is the order of accuracy of the scheme? So here you can see the first term, derivative term, which is leaving. So here you can see the delta x1. So therefore the power of this delta x is like 1. So therefore how do we simplify is, so f of x plus delta x minus f of x divided by delta x. So like you can take minus or plus, you can take, so order of delta x, which is equal to dou f by dou x of f of x. Okay, so the order of first order like accuracy. So basically the forward difference is of first order accurate scheme. Now let us actually replace in terms of index notation. So if we replace in terms of index notation, so what do we have? So we'll take it as x is equal to I and delta x as let us take it as 1. So in this scenario, so the above equation we can modify it as, so dou f by dou x at I is equal to, so f of I plus 1 minus f of I divided by delta x. So since it is of only 1D, so basically we have I in the function. Okay, let us expand it to 2D actually. Okay, so how do we expand actually? Let us see continuity equation. Okay, so why actually we are deriving first order derivatives? So in our continuity equation, so we have, let's say, dou u by dou x plus dou v by dou y is equal to 0. Okay, so let's apply the concept of forward difference to the continuity equation. Okay, so what happens we will see. So how do we write initially? So u of x plus delta x minus u of x divided by delta x plus v of y plus delta y minus v of y divided by delta y is equal to 0. So this is what we have for the two-dimensional equation. Okay. So now let us write in index notation. Okay. So before that, let's draw the grid actually. So you will see in terms of two-dimensional grid. So let us take this point. Okay. So let us take it this one as I comma j. So this point is I plus 1 comma j. Okay. So previously we have taken 1D. So for the 1D element, so here these are the index notation. So this is for 1D. So if you take this as I, this will be I minus 1. So this will be I plus 1 and this will be I plus 2. Okay, this is 1D element. Similarly, if you take this as 2D, so you can see I comma j. So this I plus 1 comma j. So here you can see I minus 1 comma j. So we are varying only along x-axis. That's why. So you can see that the j term is not varying. So if you see the point above this, so what we have is, so I comma j plus 1. So here for a constant x-axis, so we are varying y coordinate. That's why I comma j plus 1. So this point is the point where we vary both x and y. Here I plus 1 comma j plus 1. So similarly down here you can see what do we have. So I comma j minus 1 we have. Okay. So these are the neighboring points of the point of interest. So basically we say the point of interest is I comma j. So point of interest in a sense the location at which you want to calculate the flow properties. So therefore what are the neighboring points we have? I plus 1 comma j, I minus 1 comma j, I comma j plus 1, I comma j minus 1. So these are the neighboring points which we have. Now what we will do is, so we will write for the continuity equation, so in terms of the forward difference method. Okay. So here you can see u of I plus 1 comma j minus u of I comma j divided by delta x plus v of I comma j plus 1 minus v of I comma j divided by delta y equal to 0. So this is the 2D continuity equation. So here you can see for the x derivative term, so I plus 1 you have and j you have. So here you have I comma j. So here you have I comma j plus 1, here you can I comma j. Okay. So this is what we have 2D continuity equation for forward difference. Okay. So let's see for the backward difference actually. So we can see the equation. So 2. So where what we do, so when we rearrange, so we will have in terms of f of x minus f of x minus delta x divided by delta x, so which is equal to dou f by dou x plus truncation error terms. Okay, so when we rearrange the second one, so we will get the third one as in this form. So for the forward difference, you can see f of x plus delta x minus f of x divided by delta x. So similarly, when we rearrange for the backward difference, so we get f of x minus delta x by divided by delta x. Okay. So let's write down our continuity equation for the backward difference. Okay. So if we write down the continuity equation for the backward difference, so what do we get is, so u of I comma j minus u of I minus 1 comma j divided by delta x plus v of I comma j minus v of I comma j minus 1 divided by delta y is equal to 0. So this is what we have the continuity equation for the backward difference. Okay, so let us take the equation 1 and 2 of the Taylor series. So f of x plus delta x and f of x minus delta x, and if we subtract, what happens? So if we subtract these equations, so we'll get f of x to f of x. So here plus dou f by dou x into delta x divided by 1 factorial minus dou f by dou x to delta x divided by 1 factorial plus dou square f by dou x square into delta x square divided by 2 factorial plus dou square f by dou x square into delta x square divided by 2 factorial plus so on plus so on. So when we do subtraction, what happens? This term will get cancelled. So these two terms will add up. So these two terms will get cancelled. So here you can see that. So when you are making the equation 1 minus equation 2, so f of x term is getting cancelled and the second order like the even derivative terms are getting cancelled. So finally what do we have? F of x plus delta x minus f of x minus delta x is equal to 2 times of dou f by dou x into delta x divided by 1 factorial plus truncation error terms. So when we rearrange, so we get dou f by dou x is equal to f of x plus delta x minus f of x minus delta x divided by 2 delta x plus, so the order of accuracy here will be delta x square. Okay, so for the first order derivative term, so we have the order of accuracy of delta x, like let's say for forward difference and for the backward difference. So if you take the second order, like let's say central difference, so for first order central difference, So what do we have is like we have the order of accuracy of 2. Okay, so delta x square. Now let's apply this central difference for the 2D continuity equation. Okay, for the 2D continuity equation, so let us again see the mesh. J I minus 1 comma j I plus 1 comma j I comma j minus 1. This will be I comma j plus 1. So what is the 2D continuity equation we have? Do u by dou x, sorry, by dou x plus dou v by dou y is equal to 0 here. Okay, so when we apply the central difference, so this will be u of I plus 1 comma j minus u of I minus 1 comma j divided by 2 delta x. So the stencil size, so basically we say the difference between this is, let us take this is delta x and this is delta x. So the addition of delta x, this will be 2 delta x. Similarly, you take the stencil size of this one, delta y. So that would be 2 delta y plus v of I comma j plus 1 minus v of I comma j minus 1 divided by 2 delta y is equal to 0. So this is the equation which we have for 2D continuity equation in terms of central difference. Okay, so let's actually compare all the three equations. So which is a forward difference and which is backward difference and which is central difference for the continuity equation. Okay, so here let us write forward difference. Forward. Okay, so what do we have to the continuity equation? So u of I plus 1 comma j minus u of I comma j divided by delta x plus v of I comma j plus 1 minus v of I comma j divided by delta y. So which is of order of accuracy. So here you have delta x comma delta y. Okay, so this is for the forward difference. Okay, so which is like dou u by, sorry, this is equal to 0. So this is what we have. Let's see backward difference. So for the backward difference, we have u of I comma j minus u of I minus 1 comma j divided by delta x plus v of I comma j minus v of I comma j minus 1 divided by delta y. So similarly here we have order of accuracy delta x delta y equal to 0. Now let us see central difference. For the central difference, we have u of I plus 1 comma j minus u of I minus 1 comma j divided by delta x plus v of I comma j plus 1 minus v of I comma j minus 1, sorry, 2 delta y plus order of accuracy of delta x square comma delta y square equal to 0. So you compare these equations forward, backward and central. So what do we get actually? So here the stencil size is delta x delta y and the backward difference also delta x delta y. So the forward and backward difference have an order of accuracy of first order. Okay, for the central difference, so we have the order of accuracy of delta x square, so which is of stencil size 2 delta x and 2 delta y. Okay, so this is what we have for the 2D continuity equation. So for the 2D continuity equation, we have applied our forward, central, and backward difference. Okay, so in the next session we will take the momentum equation for the that is one more tutorial question. So for the momentum equation, so how do we apply the same concept of the forward, backward, and central difference, and what are the additional terms we have here in the apart from the forward, backward, and central difference that we will see, and we will actually conclude the tutorial question of third module. Okay, when we see the module. When we see the momentum equation. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.